thank you for joining. So as Anita already said, I'll be talking about majority dynamics on the binomial random graph. And this is joint work with Nikolaos Fontolakis and Mihan Kung. Majority dynamics is a graph process. In this process, every vertex is assigned one of two colors, red and blue. And we start out from an initial assignment. So we partition the vertices into red vertices and blue vertices. And then in every step of the process, every vertex looks at all of its neighbors, determines which color is the majority within its neighbors, and adopts this color. Now, this isn't always possible. It can be that there is a tie within its neighborhood, and then it just keeps its current color. And we can run this process forever. Now, it turns out that it's not actually necessary to run forever, because after a while, we'll stop seeing anything new. Goes and Olivos showed that after a sufficient number of steps, the process will become too periodic, meaning that the color of every vertex will match its color from 2 steps before. Obviously, for certain vertices, it can also match the color in the previous step as well. It's not necessarily switching between the 2 opposites in every step. So here's a quick example. I have my small graph. I assign initial coloring to every vertex. So for example, this vertex here has 2 blue neighbors and 1 red neighbor. So this one will become blue after the first step, and we evaluate what happens to all the other vertices as well. So several vertices change colors. And here's an example for a tie. So this vertex has 1 blue neighbor and 1 red neighbor. So it will keep its red color even in the next step. And we can keep going on, but it turns out that the configuration so this configuration matches what we had 2 steps before, meaning we actually reached the sufficient number of steps stated in the theorem of Goels and Olivos. And that means that from this point on, we're just switching between the last 2 configurations. Majority dynamics closely resembles the K-Walter model. So in case of the K-Walter model, K is an odd integer. It's a parameter of the model. And here also every vertex has 2 possible colors, red and blue. And again, we start out from a partitioning of the graph into red and blue vertices. The difference here is that in this case, in every step, every vertex selects K random neighbors. And because K is odd, there is a clear majority here and adopts the color of the majority. Now, it's also possible that this doesn't work, but this is due to the fact that not every vertex has to have K neighbors. So if a vertex has less than K neighbors, then we use all of the neighbors if the number of neighbors is odd. However, if the number of neighbors is even, we randomly select one, leave that one out, and decide the majority within the remaining set of the neighbors. Again, one can run this process forever, and the connection to majority dynamics is evident when one takes K to be large. So if K is n-1 or n, depending on the parity of n, where n is the number of vertices in the graph, then the 2 processes match, except in the manner in which ties are resolved. So in majority dynamics, in case there is a tie, then we select the, so then we keep the current color of the vertex. However, in the K-Walter model, the color of the vertex is blue with probability 1/2 and red with probability 1/2. So we'll be analyzing majority dynamics on the binomial random graph GMP. So this is a random graph on n vertices where every edge is inserted independently with probability p. And for majority dynamics, it turns out that the average degree is a more suitable parameter than the edge probability. So we'll be using the average degree d, which is just n times p, well, roughly n times p. So Benjamin, Chan, O'Donnell, Tamás, and Tam conjectured that if we initially assign the vertex colors in GMP so independently and uniformly, meaning that each vertex is with probability 1/2 blue and with probability 1/2 red, then depending on the average degree, one of the two possible things can happen. If the average degree tends to infinity, then eventually almost every vertex will have the same color. And after that step, and in all later steps, still almost every vertex will have the same color. On the other hand, if the average degree is bounded, then we will have a red and a blue color class, each containing roughly half of the vertices after a sufficient number of steps. Now, we do start off with having two color classes roughly of the same size. And it would be really strange if somehow one of the color classes increased its size and then went back to two color classes being roughly of equal size. But the conjecture technically allows this. The difficulty in proving this conjecture has multiple reasons. The first one is that this is a non-monotone process. It's non-monotone in two senses. First, the color of a vertex can change multiple times. And the second one is that if one considers the graph property that starting out from an initial configuration, I end up in a configuration where almost every vertex has the same color, this is non-monotone. Simply adding or removing edges from the graph can have a significant effect on the behavior of the process. And the second reason is that the steps are very interdependent. So already to establish what the colors are after the first step, we have to expose the initial color of every vertex. And in addition, we have to expose every edge in the graph. This means that there's basically no probability left for the later steps. Benjamin, Chan, O'Donnell, Tamás, and Tan didn't only state the conjecture, they gave a partial proof. So we're assigning the initial colors uniformly and independently. Then when the average degree is larger than lambda times root n, where lambda is some large enough constant, then in 4 steps, every vertex will have the same color. The only problem is that instead of showing this with high probability as the conjecture would like, they show it with probability at least 0.4, which is smaller. Since that proof, many people have studied the process, but most results assign the initial vertex colors in a different manner. So the first result is due to Zemakan, and he showed that, again, majority dynamics in GMP, and the initial colors are still assigned independently, but instead of uniform probability distribution, he gives the blue colors a small bias. So he wants blue probability to be 1/2 plus an omega 1 over square root of d term. And in this case, when the average degree is at least 1 plus epsilon times log n, meaning that we're above the connectivity threshold of the binomial random graph, then with high probability, every vertex will be blue in a constant number of steps. The next result is due to Tran and Wu, and they also consider majority dynamics in the binomial random graph, but they just want that there is a difference between the number of blue vertices and the number of red vertices. In particular, they want this difference to have size 2 times bn, or the number of blue vertices to be n over 2 plus bn. And when the average degree is constant times n, then they provide a lower bound on the probability that every vertex will be blue at the end of the 4th step. And this probability basically depends on a constant which only depends on c, and then the maximum of 1 over n and 1 over bn squared. So essentially what they say is that if the difference between the number of blue vertices and the number of red vertices tends to infinity, then with high probability every vertex will be blue after 4 steps. So based on these results, one can see that in the binomial random graph model, at least for a large range of the average degree, there is a tendency for the majority dynamics to reach a unanimous or almost unanimous state. However, this isn't the case for other random graph models. So for example, Benjamini, Chan, O'Donnell, Tamás, and Tan showed that if we consider the 4 regular random graph and we assign the initial colors independently and uniformly, then there is no possibility for unanimity. So with high probability, unanimity will never occur. In fact, we don't have to assign the blue and red vertices each with probability 1/2. So if the probability that a vertex is initially colored blue is anywhere between 1/3 and 2/3, this still holds. Since I mentioned the K-water model, since I mentioned earlier the K-water model, I would like to mention that it also has been studied in GMP. So in the K-water model, one usually takes a fairly small constant as the parameter K. And in this case, one can take any K which is at least 5, and there's a constant. And if we give blue a slight advantage, meaning we're coloring every vertex blue with probability between 1/2 and 1, but it has to be bounded away from 1/2. Then if the average degree is at least 2 plus epsilon times log n, then with high probability, every vertex will be blue eventually. So let's go back to the conjecture of Benjamini, Chan, O'Donnell, Tamás, and Tan. And essentially, we show that this conjecture holds in the binomial random graph when the average degree tends to infinity significantly faster than root n. And in particular, in this case, we will have that every vertex is the same color, so not just almost every vertex, and it is reached within 4 steps. In the remainder of this talk, I will try to justify why this result holds. And we are going to have to analyze the 4 steps of the process. I will split the proof into 2 parts. I'll first look at the first 2 steps. This is the more difficult part, and then I look at the last 2 steps. And in the first 2 steps, we get from essentially having 2 color classes of the same class to almost every vertex having the same color. We'll use a second moment argument for this. And in the last 2 steps, we'll show that we can get from almost every vertex having the same color to actually every vertex having the same color. So I would like to remind you that we have 2 sets of random variables. One is for the initial colors of the vertices, and the second one is for the edges of the random graph. The order in which we expose these random variables is, well, at least for our proof, it's very important. And basically, we start by exposing the initial color of every vertex, and then we will gradually expose the edges within the graph. So let's see how this goes. So we're given the vertices in the graph, and as I said, we start by exposing the colors of the vertices. So the number of blue vertices in the graph is a binomial n 1/2. This means that with high probability, the difference between the number of blue vertices and the number of red vertices will be of order √n. And let's just assume for the remainder of the talk that there are more blue vertices than red, although the picture doesn't completely represent this. So we want to know what's the probability that a vertex will become blue after 2 steps. So let's pick our favorite vertex V. And in order to establish this probability, we will need to know how the neighbors of V behave. So we look at the neighbors of V, expose these edges, but only these edges so far. And then we pick our favorite neighbor of V, let's say U. And from this point on, we'll only be interested in edges adjacent to U, so we can forget about the other edges adjacent to V. And we have this set of leftover vertices, so everything which isn't U or V. And now we partition this set of vertices into 3 parts. So we will have the set of red vertices, the set of blue vertices, and in the blue vertices, we also split it into 2 parts. So we want a set of blue vertices which contains exactly as many vertices as the set of red vertices does, and whatever is left should be in WB+. And because the number of blue vertices in the graph exceeds the number of red vertices in the graph by √10, so we know that WB+ has size roughly √10. Okay, so we'll now use this to calculate the probability that U is blue after 1 step. So let's ignore the effects of the initial color of U, V, and the vertices in WB+. Then the probability that U will be blue after 1 step is 1/2. It's basically saying that I have 2 random variables which have exactly the same distribution, and I'm just asking what's the probability that one is larger than the other. Okay, so now let's take the effect of the neighbors of U in WB+ into account. Well, each neighbor U has in WB plus will increase the probability that U will be blue after one step. In particular, we can use the local limit theorem to show that this probability is of order 1 over root D. Okay, but U actually has many neighbors in WB plus. And the reason is that the expected number of neighbors is obviously of order root n times P, and this is B over root n. But because of our choice of D, so D tends to infinity faster than root n, that means that the number of neighbors of U in WB plus also tends to infinity. But this is a binomial random variable, so it will be concentrated around its expectation. So with high probability, we have something that's the same order as the expectation. Now, so far we have ignored the effects of U and V has on this probability, but we can actually ignore this. So if we sacrifice two neighbors of U in WB plus, this would cancel out any effect the initial color of U and V has on the probability that U becomes blue after one step. But because we have so many neighbors in WB plus, sacrificing an additional two doesn't make much of a difference. So based on this, we know that the probability that U will be blue after one step is 1/2 plus omega of 1 over square root D. So this is the term increase we get for every neighbor of U in WB plus times D over root n, which is the expected number of neighbors. And a quick calculation gives us that this is 1/2 plus omega of 1 over square root of D. Okay, so now that we know how the neighbors of V behave, and recall that because the previous probability didn't actually care about the initial color of U and V, this holds uniformly for every neighbor of V. We can...
Hi, sorry, quick question. Is V an arbitrary vertex at this point, or did you already say something about it?
So V is an arbitrary vertex.
Okay, thanks.
Okay, so we want to know what's the probability that V is blue after 2 steps. So we want to know what's the probability that, so we want to examine the random variable X, which is just the sum of its blue neighbors. So we already, okay, so since we're in a binomial random graph, with high probability, the degree of V will be close to D. That means that based on our previous calculations, we can, we know the expected value of X is just the degree of V divided by 2 plus an omega root D term. So now if we were able to find an upper bound on the variance of X, then we could use Chebyshev's inequality to give a lower bound on the probability that V is blue. And if this upper bound is of order D, then V would be blue after 2 steps with high probability. So let's calculate the variance. So X is the sum of indicator random variables. The important part to calculate is the covariance of the pairs of indicators. So far we have exposed the initial color of the vertices, and this is where exposing the initial color of the vertices before the edges will become very important. And we have also exposed the neighbors of V. Now, if I were to look at U and U prime, so the edges on which u becoming blue depends on are the ones adjacent to u, and similarly for u prime. But these two edge sets are disjoint except for one possible edge, which is the edge between u and u prime. So we can actually use the probability of this edge as an upper bound of the covariance. And that means that the covariance would be of order d over n. Unfortunately, this would lead to a variance which is of the order d cubed over n. And for our range of d, this is much, much larger than d. So we don't actually have a variance of the right order of magnitude. So let's take a closer look at the covariance. So we're talking about the covariance of indicator random variables here. And if we have two events A and B, and we look at their covariance, and we can express A and B as the disjoint union of events AI and Vj. This means that we can express the covariance of the indicator of the event A and the indicator of event B as the sum over all possible pairs AI Bj, the covariance of the indicator of AI and the indicator of Bj. However, many of these covariance terms can be zero. In particular, if AI and Bj are independent, then the covariance terms are zero. So we actually only have to consider pairs AI and Bj where AI and Bj are dependent. So we're going to break up the event that vertex u will become blue after the first step into two parts. One is nu. So in this case, we already know that u will be blue after exposing all of its neighbors except for the u prime edge. So if there's a clear enough majority in this edge set, then we don't actually care about whether the edge u prime is present or not. And the second one is that u is blue, and we actually need to expose the edge between u and u prime. Okay, so what does this mean for dependence? Well, nu and nu prime are independent. Nu is depends only on the edges adjacent to u, except for the u prime edge, and nu prime similarly depends only on the edges adjacent to u prime, except for the u prime edge. These two sets of edges are disjoint, and because we're in GMP, their existence is independent. Okay, so what about nu and cu prime? Well, for nu, we have to expose the edges adjacent to u, except the u prime edge. For cu prime, we need to expose the edges adjacent to u prime, this time including the u prime edge. But we're only exposing each edge once still, so these two events are independent, and by symmetry, so is the event cu and nu prime. What this leaves us with is the indicator of cu and the indicator of cu prime, and this turns out to be of order 1 over n. Now this means that the variance of x is of order d plus d squared over n, but because d is smaller than n, that's just order d, which is the right order of magnitude. So we have that with high probability we will be blue after 2 steps, but we can use Markov's inequality to show that with high probability every vertex, almost every vertex will be blue after 2 steps, because V is an arbitrary vertex. Okay, so we now know that after 2 steps, almost every vertex are blue. So we can have only a small set of red vertices, so only little of n red vertices. And from this point, we are basically doing a union bound on every possible set of red vertices. And this tells us that after the third step, well, we cannot completely eradicate the number of red vertices, but we can show that there's a significant decrease in them. There's at most little of the red vertices left. But this then gives us that in the fourth step, there cannot be any red vertices, because in order for a vertex to become red or stay red, you need to have at least half of its neighbors to be red. Now we're in GMP, so, and they're sufficiently large. This means that every vertex has degree roughly d. So in order for it to have roughly d over 2 red neighbors, we would actually need to have d over 2 red neighbors in the graph, but because there are only little or d red vertices in total, this is impossible. And that basically completes the proof. So if we were trying to reduce the size of D, then this proof breaks down for multiple reasons. And let me just highlight some of the most important ones. So first of all, it seems that the smaller the average degree in the graph is, the more steps one needs in order to reach unanimity or almost unanimity. It seems that this root n is the lower bound of having 2 steps, and below this we would need at least 3. And nobody actually managed to analyze the process for 3 steps, where in the first 2 steps one still has roughly n over 2 red and n over 2 blue vertices. The probability calculations are upset. So first of all, when D is large, we had that our vertex had many neighbors in WB+. This will be no longer true. Some vertices will have a couple of neighbors, but most will have none. And this somehow has to be taken into account. Unfortunately, this has a side effect, because we could treat every vertex uniformly in this case, but this will no longer be true, simply because we don't have many neighbors in WB+, and we are unable to cancel out the effects of the of any already exposed neighbors. And there is a final one, which, as I mentioned at the beginning, the process becomes too periodic. But this actually shows up in the probability calculations. So if I had a vertex which was initially blue, then after 2 steps, it will be much more likely to be blue than red. And finally, we're really unsure how one would generalize the variance calculation, in particular how one would do the restriction on the probability space. So how to find those 2 independent events. This is due to the fact that we are no longer just looking at the edges adjacent to u and u prime. We would need to look at every path of length to starting from u and u prime, and there are much more chances for these to interact. I would like to finish the talk by mentioning 2 open questions. So the first one is rather obvious. prove the conjecture of Benjamini, Chan, O'Donnell, Tanmus, and Tan for smaller d. And the second one is concerning the minimal difference between the initial color classes, which is needed to lead to unanimity with high probability. So in our proof, we're strongly relying on the fact that we have two color classes at the beginning, and one is larger than the other by an additional, so one contains root n vertices more than the other. Can this root n term be decreased? So the result of Tran would seem to imply that this is the case. So when d is a constant times n, then already if the difference is already an arbitrary function tending to infinity, then with high probability, every vertex will have the same color after 4 steps, but it's not clear what if this is minimal, and if similar bounds are possible for the remaining average degrees. Thank you for listening.
Thank you very much. Let's all unmute and thank Tamás by clapping. Thanks. Are there questions for Tamás?
Yeah, I have a question. So with Markov chains, if you want to break the periodicity, you usually have a sort of stay put probability. So I was just spending the last couple of minutes thinking whether something like that could be added here. I guess if maybe at every step there's a small probability that the vertex does nothing, but then it's a completely different process, and I'm not sure if anyone's interested in that.
I mean, the vertex stays put with some probability. It's just that it depends on its neighbors. If the majority of its neighbors is the same, then it stays put. But
sure,
adding an additional one to it.
But if you just wanted to break the two periodicity. So
I know that an asynchron version of the K-Water model exists. So there each vertex is assigned a timer, and it wakes up and then makes its change according to the rule. So this would mean that every other vertex stays put at that point. I don't know if majority dynamics has a similar version, but I think that would be closer to what you're describing.
Yeah, no, thank you.
Thank you. Are there more questions?
I have a question. First of all, thank you for using blue as the winning color. So I had a question, although you kind of answered it, it may but just be an observation then. I'm wondering what happens if you condition on two colors being of the same size. So there are ways to do that. You can either plant a red set of size n/2, or maybe what you could do is partition vertices in pairs randomly, and then one is red and another one is blue. But anyway, if anything known is known there, for instance, there's a positive probability that you have the genuine periodicity, or maybe some property of the distribution that guarantees that blue color wins, or something.
I don't actually know what happens when you do exactly n/2, n/2. So that hasn't actually been studied up to this point. I mean, I guess it would be the probability that blue wins is 1/2, and the probability is red wins is 1/2 by symmetry, or it stays somehow. Both sets stay close to n/2. I don't think anybody studied that until now.
Thanks. And another question would be about the time of consensus. So we mentioned, for instance, for sparse graphs, it's very difficult to say anything. So is it maybe possible to get a bound if you have an expander graph or a random graph say we don't know what happens, but in a constant number of steps, we do reach consensus?
So it's so no, it's not known if I mean with this sorting distribution, it's not known. So I mentioned the result of Zemakan. So he made a bias towards blue, which then resulted in a quick the blue winning quickly, basically. But it's, yeah, it really depends what your starting distribution is.
And for which graphs is Zemakan's result again?
So Zemakan did everything for everything above the connectivity threshold. So when the average degree is larger than log n. So, but it's basically a very large bias on the initial vertex sets. Still tending to 1/2, but the omega 1 over square root d term is it would result. So we're conditioning on root n difference. This one would result in a n over square root of d difference. So it would match ours only when d is n.
Tamás, there's a comment by Omar in the chat. He says this should cause a one-step delay in consensus.
I think he is referring to the balanced color assumption there.
Yes,
Yeah.
this was about starting with a balanced configuration.
Okay.
But proving this is not at all clear how to do. But that would be the expectation.
So you would want to use the kind of anti-concentration at the level of each neighborhood to prove that, or?
So morally what happens is that once you have a slight bias, the dynamics amplifies it. And so as we've seen in Tamás's talk, if you have a square root n discrepancy, then after 2 steps, it's amplified to almost nothing, to almost everything. So if you start with 1/2 and 1/2, if you condition it being 1/2 and 1/2, then it's fairly straightforward to see after 1 step, you'll get again a square root n discrepancy.
Yes,
but of course, at this point, it's no longer independent of the graph, so you can just repeat the proof and argue that after 2 more steps, you have a high fraction of blue. But that would be I think I would be very surprised if that's not the case.
Okay.
I just, Tamás, I was wondering if you've seen the talks for Random 2020, which are happening at the moment. There's a new paper by Tran and Vu.
I mentioned that one.
Oh, you did? Okay, sorry.
It's this one. Or is that
no, I think it's, oh wait, Bn can be a constant. It says that if you have just some constant number of extra vertices is enough.
Yes, Bn can be a constant.
Okay. All right, thanks.
Yeah, it's that paper.